Let's do a quick recap. Again, we were trying to estimate overhead cost based on repair hours, and we gathered our data, 15 months worth of data. First thing we did was we plotted it using a scatter graph. Then we right-clicked on one of the data points, and we could add a trend line. And in adding that trend line, we could specify that we wanted to include the equation and the R-square on the chart. Alternatively, we could use Excel's function, R-square, slope, and intercept. For instance, on our slope function, we basically wanted to estimate our overhead cost, which was our dependent variable, using repair hours, our independent variable. Of course, both methods give us the same results. Our R-square, how do we interpret that? Basically, we were saying that we could explain roughly 83% of the variability in cost using repair hours. We could have observed from our graph that we had a pretty decent R-square because these points are fairly closely clustered around our line. What we can't tell from these functions or our trend line with the equation up top is how significant either the slope or the intercepts are. Let's in particular look at, is this slope of 12.5, is that really the variable cost per repair hour? And we know the answer to that is no, it's not really the variable cost per repair hour, because if we had slightly different data, let's say we only had 14 months worth of data, we would have gotten a different estimate for our slope. If we had had 16 months worth of data, again, we would have gotten a different estimate for our slope. However, given our 15 months of data, our best estimate for the slope coefficient is 12.5. Let's look and see how significant that is. In order to do that, we would want to use Excel's data analysis functions and run a regression. We have our output for our regression right here below. And again, it provides us with the same estimate for our intercept, repair hours, and our same R-square as we had using the Excel functions. Now, however, it gives us additional information, the standard error and t-statistic for our intercept and for our repair hours. Let's take a look and see what that t-statistic means for repair hours. Basically what that means, or it's calculated by taking our estimated coefficient, dividing it by our standard error, which is basically one standard deviation away. That's where we get the 7.904. Let's look and see how we interpret that. If you recall, the area under the normal curve can be defined as follows. If we go out plus or minus one standard deviation, roughly we would expect, by chance, looking at normal data, that 68% of the time the value would fall between plus or minus one standard deviation. 95% of the time we would be between plus and minus two standard deviations. If we go out 3 standard deviations, we've basically captured 99.7, almost all of our data. There's still a little bit of data way out here in the tails, basically 0.15 on each side, but basically we can feel pretty certain that if we're out here in the tails, that our null hypothesis, which is that our slope coefficient really is 0, is false. So our best estimate of our slope coefficient was 12.5, so that's our x bar. If we go out plus or minus one standard deviation, we would have said it would have been somewhere between 11 and 14, about 68% of the time if we gathered different data. 95% of the time it would be between plus or minus 2 standard deviations, or as low as 9.5, as high as 15.5. We could feel very, very confident, over 99% confident that the slope coefficient, had we gathered more data, would have been somewhere between 8 and 17. In fact, we asked the question, what's the chance that it's really 0? And again, 0 would have been somewhere way, way out here in the tails, absolutely, positively close to nothing. And that's what that p-value is telling us. If we look at that p-value, we're basically saying that there is a 0.000000003 chance that the true value for our intercept is 0. In other words, we're saying we can feel very confident that not that it's 12.5, but that it's not 0. And given our data, our best estimate is that it's 12.5. Let's go ahead now and take a quick look at multiple linear regression if we want to perhaps get a slightly better estimate. So in addition to repair hours, we've gathered information on part costs. And using our Excel functions, we've estimated an R-square using repair hours to explain overhead cost and part cost to explain overhead costs. Individually, again, our repair hours explained 83%, our part costs only explained 78%. So if we were to choose one variable, we would probably choose repair hours. But what if we ran a regression that included both of these? In other words, we ran our multiple linear regression. Let's take a look at that output and interpret our output. First thing we're going to do is look at our R-squared. Notice we are explaining more of the variability in cost. Instead of only 83% using repair hours, using both part cost and repair hours, we can explain 89% of the variability. We might want to take a look, though, at our adjusted R-square, because the truth of the matter is it doesn't matter what we add as an additional independent variable, we would always get a slightly higher R-square. Our adjusted R-square accounts for the fact that we lose what we call a degree of freedom every time we add one more independent variable. So our adjusted R-square for both variables in our model is 87%, and we can compare that with the R-square we had for our single variable model. For our single variable model, our adjusted R-square was 81%. So we can feel pretty good that we've got a slightly better model using both variables. Whether or not we would want to use this depends on the cost of attaining different or additional data related to part costs in addition to repair hours, and that evaluate that cost-benefit trade-off. Let's look at the significance of both of these additional variables. Repair hours. By itself, recall, we estimated repair hours, the coefficient would be 12.5. We've got a different estimate now for our repair hours because we've got an additional variable in our regression equation adding an additional information. In terms of our standard error, we would still say that our repair hours is a relatively significant variable. Our t-stat is 3.5. So in other words, it is 3.5 standard deviations away from 0. If we looked at the data under our normal curve, again, we came out with an estimate of 7.8. Our standard deviation was basically 2.2. So going plus 1 standard deviation, 10, minus 1 standard deviation would have taken us down to 5.6. So we basically say 68% of the time, given our data, we would expect to fall somewhere between these two. We go out to plus or minus 2 standard deviations, we would have been 3.4 to 12.2. 3 standard deviations, 1.2 and 14.4. What's the chance that the real slope coefficient for repair hours is now 0? Well, that would be way out here on the tails. Basically, 3.5 standard deviations away, and there's only a 0.004% chance that the real slope coefficient for our two variable model would be 0. So we can feel pretty confident that repair hours belongs in our model. How about part cost? Part cost, we're saying that every time we spend another 67 cents on part costs, every time we spend another dollar on part costs, our overall cost of overhead goes up by 67 cents. So standard error of 0.25, t-stat 2.675. Again, let's look at that area under our normal curve. So our best estimate of our slope coefficient was 67 cents or 0.67. We go up plus 1 standard deviation takes us up to 0.92, 1.7 at 2, 1.42 at 3. If we go down 1 standard deviation, we drop to 0.42. Down 2 standard deviations, we'd be at 0.17. Down 3 standard deviations, we'd be at minus 0.08. So notice, our null hypothesis is that the true coefficient is 0, and 0 falls somewhere in between minus 3 and minus 2 standard deviations away, which is consistent with our regression results, because if we took our slope coefficient of 0.67 and we divide it by our standard error of 2.5, that's where we got our 2.675 standard errors away. Notice we still have a real good p-value. If we wanted to be 5% certain, well, this is at the 0.02%. So 2% certain that this is truly different than 0. We're not saying that we're 98% certain that it's 6.7. We're just saying that 6.7 is our best estimate, and there's only a 2% chance that the real value is 0. Let's go ahead now and answer some questions. How much of our variability can be explained by repair hours? Again, that would have been the R square only looking at repair hours. Our R square only looking at repair hours was 83%. So 83%. How much of our variability can be explained by part cost? This was the 78%. And again, that was the R square right there using just part costs. Which independent variable is best at predicting in a simple linear regression? Well, our best predicting variable in the simple linear regression was our repair hours. It had the higher R square. How much of their variability can be explained by our combined model? That was our R square for our multiple linear regression. Our R square for our multiple linear regression was 89.2. So 89.2% can be explained. Is the combined model, in the combined model, which independent variable is most significant? And again, we had 2 independent variables, repair cost and repair hours and part cost. We would say the most significant one is repair hours because it has the higher t-stat, or alternatively, meaning the same thing, the lowest p-values. So it's repair hours. And finally, what's our overhead cost that we would estimate for if we were going to have 400 repair hours and spend $2,500 on parts? Our equation is simply y equals our intercept, our plus our slope coefficient for repair hours, which was 7.782, multiplied by the number of repair hours we expect to incur, plus our slope coefficient for part cost of 67 cents, times the $2,500 we expect to spend on parts. So our best estimate for overhead cost for 400 repair hours and $2,500 in part costs would be a total overhead cost of $11,250. Let's walk through a couple problems. Problem 536. Give you a chance to read through it. And let's then go ahead and answer the question. What percentage of our variation in overhead cost is explained by the independent variable? Our independent variable in this case was direct labor hours. And we see our R square is 0.848. So what percentage of our variation was explained by it? This would be 84.8%. So our equation for estimating our overhead cost is $120,000 for our intercept plus $5 per direct labor hour. And if we were going to be working 50,000 direct labor hours, we would take 5 times our 50,000. Add to it the 120, and we get an estimated overhead cost of $370,000. To answer C, how much of the variable manufacturing cost per unit using our variable whole overhead estimated by the regression, we're going to have to first calculate the direct material cost and the direct labor cost per unit. So let's go ahead and see how we would do that. We're given our total direct material cost and direct labor cost, assuming we produce 20,000 units. So we're going to take the 800,000 divided by 20,000 to get the direct labor cost per unit. And we're going to take the 640,000 divided by 20,000 to get the direct labor cost per unit. Direct material cost will be $40 per unit, direct labor $32 per unit. Then we need to calculate our estimated variable overhead per unit. Recall, and we need to be careful here, it took us 40,000 hours to make these 20,000 units. So it's taking us 2 hours to produce every single unit. And our slope coefficient was $10 per unit. Rather, $5 per direct labor hours. So we're going to want to simply take that 2 hours per unit, and again 40,000 hours in total, meant 2 hours per unit, times our 5, and we get an overhead cost of $10 per unit. So total variable cost per unit, the 10 plus the 32 plus the 40, our estimated overhead cost per unit is $80. Our estimated overhead cost is rather $82 per unit. And again, that was simply the direct materials of 40, direct labor of 32, and variable overhead of 10. Next question wants to know our contribution margin. We're selling our product for $96 per unit. We had variable cost of $82 per unit. And I don't see anything mentioned regarding selling costs. So our contribution margin is 14, which is the 96 selling price minus the 82. Our total manufacturing cost equation implied by these results, if we're doing it again in terms of number of units, we had a fixed overhead component of 120. So we know that it's one of these two. And our variable cost per unit was $82, and we see we don't have one here. It would have been some other equation, which is if we're doing this in terms of number of units, we've got our fixed component of $120,000 plus the variable cost of $82, not per direct labor hour, but rather per unit. Let's take a quick look at problem 550. In our standard regression equation, y equals a plus bx, b is described as, it's our slope coefficient. It's the variable cost coefficient. So it would be 5. The letter y is best described as what? The y is our dependent variable. The letter x, that is our independent variable. If the controller uses the high-low method, we're not going to bother about the high-low method. You can go through our high-low method. But again, you want to use the high and low months in terms of credit hours, our activity, not the high and low in terms of cost, but the high and low in terms of activity. But you should get the equation number 1. Let's take a look at the next thing they're asking about. Our best estimate based on 2,100 credit hours and our regression results, we're going to take our intercept of 404,874, add to that 207 times 2100 credit hours. And we get the 839,575 as our answer. Our correlation coefficient for our regression for administrative costs, again, our correlation coefficient, that was that crazy one we said it was just simply the R, the multiple R, which is really just our R. So it is the 0.9338. And notice if we square that number, of course, we get the R squared.